Assalamualaikum. So today our group will be presenting a video presentation about magnetic levitation trains. This is our group members. The first one is Ms. Levitation, which is me, and I'm gonna talk about the introductions of Maglev. Next is Raisa Nuridina, where she's gonna talk about the explanations of Maglev technology. And there's Alia Hana, where she's gonna talk about the examples, benefits, and challenges of Maglev. And lastly, we have Nordiana Alian, and she's gonna talk about the developments and innovations. What is Maglev? Maglev, or magnetic levitation, is a technology that is a cutting-edge transportation, and this innovation allows trains to float and hover above tracks using magnetic forces. By eliminating physical contact between the train and the track, Maglev system achieve unparalleled speed, efficiency, and smoothness. There is two primary principles used for these systems. The first one is electromagnetic suspensions, which is EMS, and electrodynamic suspension, EDS, which enable the train to levitate and propel without friction. Maglev trains represent a significant advancement in the transportation industry, combining physics, engineering, and advanced control system to create an efficient alternative to conventional railways. The concept behind Maglev is rooted in the principles of magnetism, where opposing magnetic fields create lift and propulsion, offering a glimpse into the future of sustainable, efficient, and ultra-fast transportation. Next, we're going to talk about the significance of Maglev trains. The first one is high speed and reduced travel time. As Maglev trains can reach speeds exceeding 600 km per hour, which is equivalent to 373 meter per hour, drastically reduce the travel times compared to the traditional rail or even air travel over short distances. For instance, the Shanghai Maglev can transport passengers between the city center and the airport in just 7 minutes, a trip that would take significantly longer using car. Next is the second one is energy efficiency and environmental impact. As Maglev system are more energy efficient at high speeds as they eliminate rolling resistance from wheels. These trains can run on electricity from renewable sources, reducing carbon emissions compared to fossil fuel-powered transportation such as car. And the next one is low maintenance costs. As the Maglev trains doesn't have the mechanical components like wheels and axles, this can reduce the cost of causing by the wear and tear. Magnetic maintenance costs are lower over the long term, making Maglev system more sustainable despite high initial investment. Other than that, we also have technological and economic innovation. The development of Maglev systems drive innovations in material science, magnet technology, and engineering. Hence, these projects can boost economic development by creating jobs and modern infrastructure. And lastly, we have comfort and noise reduction. As the Maglev trains has no physical contact between the train and track, these trains offer a quieter and a smoother ride. The vibration and noise that commonly happen in conventional rail systems are significantly reduced in Maglev. We have the electricity and magnetism concept used. The first one is electromagnetic induction. The Maglev train relies on the fundamental principle of electromagnetism. When electric current flows through a conductor, it creates a magnetic field around it. In Faraday's law of induction, it stated that a changing in magnetic field induces an electric current in a conductor. By controlling the electric current flow, engineers can manipulate the strength and direction of the magnetic field. In maglev trains, the movement of magnets, either on the train or the track, induce currents in coils which generate opposing magnetic fields to create lift or repulsion. And next we have magnetic levitation. Magnetic levitation can be achieved by the repulsion or attraction of magnetic fields. Maglev train typically combine electromagnetic suspension (EMF) and electrodynamic suspension (EDS), where the EMS attractive the forces and the EDS repulsive the forces to levitate the train above the guideway. This eliminates the need for physical contact between the train and the track, hence reducing friction and allowing for high-speed travel. And lastly, we have superconductivity for some system. As it stated, some maglev systems use superconducting materials, which have the unique property of exhibiting zero electrical resistance at very low temperatures. When cooled below critical temperature, superconductors can maintain persistent currents without any loss of energy. This property is crucial for sustaining magnetic fields needed for levitation and repulsion.
So, here's a detailed exploration of magnetic levitation trains. The first patents for magnetic levitation technologies were filed by French-born American engineer Émile Bachelet in the early 1910s. American professor and inventor Robert Goddard had written a paper outlining the idea of maglev levitation in 1904. Maglev trains float on a cushion of air, eliminating friction. This lack of friction and the train's electrodynamic designs allow these trains to reach unprecedented ground transportation speeds of more than 500 kilometers per hour. So, how do magnetic levitation trains work? The simple idea behind magnetic levitation trail rail system consists of three components. The first one is a large electrical power source. Next, metal coils lining a guideway or track. And lastly, large guidance magnets attached to the underside of trains. Maglev trains do not have wheels or rails. Therefore, they float down these guideways, where the three essential parts to achieving maglev functionality is levitation, propulsion, and guidance. As you can see, there are three different types of rails or guideways. The first one are standard rails. Next, we have Transrapid Guideway, which is developed in Germany. Lastly, we have the MLX Guideway, which is developed in Japan. Two different types of levitation ways used in magnetic levitation trains. The first one is electromagnetic suspension. The attractive force of electromagnets placed on the guideway and on the train are used to achieve levitation. The benefits of this way is that it is simpler to implement compared to electrodynamic suspension. However, it is inherently unstable, where it is difficult to maintain the correct distance between the train and guideway at high speeds. Next, we have electrodynamic suspension. It uses the repulsive force of superconducting magnets placed on the guideway and on the train to achieve levitation. It is incredibly stable at high speeds, and maintaining the correct distance between train and guideway is not a concern. However, there is sufficient speed that is needed to be built up for the train to levitate, and it is more costly and complex to implement. Propulsion. Maglev uses an electric linear motor to achieve propulsion. Rotor is attached to the bottom of the train cars, while stator is in the guideway. Magnetic fields in the stator induces a magnetic field in the rotor. This interaction between original field and induced field causes the rotor to be pulled along, as you can see in the graphics on the side of the slide shows the difference between conventional railways and superconducting maglev. Lastly, we have guidance. High-speed maglev trains uses repulsive magnetic forces to keep trains centered over the guideway. For example, we have transrapid guidance, where two electromagnetic rails placed on a train is facing the guideway. Next, we have MLX guidance, where levitation rails on either side are connected to each other, where when the train moves closer to one side, a restoring force is induced and pushes it back to the center.
Is three examples of our real implementations for maglev trains. The first one is Shanghai maglev trains in China. The second one is Incheon Airport maglev trains in Korea, and the last one is Chuo Shinkansen in Japanese. There are three potential benefits of maglev trains. Maglev has high level of safety because this technology use their dedicated guideway without intersections in order to withstand a collision with smaller objects. In addition, Maglev has a perfect safety record with million kilometers of service stories. Other than that, the extent of physical contact between the vehicles and the track extends the lifespan of railroading, or also this maglev. So, as to make it less mechanical failure, electronics, which is the EMS or the superconducting magnets EDS, replace wheels and the supporting machinery. Furthermore, the maglev is well known for their incredible high-speed transportation, which is making it faster than the most popular aircraft. For example, LGV French TGV trains, which have the record speed of 578 km per hour, which cannot beat the maglev record speed 603 km per hour. However, there is a few challenges of maglev trains due to the separation from the other tracks and railway that make it limiting feasible roads because of the long stretches of the tracks. Maglev also consume high construction costs since the involvement of length and navigating regulatory hurdles for building of maglev. The limited infrastructure, maglev have significantly different system for conventional railways. It is because the requirement of the dedicated tracks that are specifically designed for them. The last possible challenge for maglev is the local ecosystem and community destruction that may occur. For instance, maglev increases net carbon dioxide emission from 218 seats to 313 seats million kilograms for a year. Lastly, the communities will consume a worsening air quality and reduction of property values.
Future developments and innovation that can be done to improve maglev is first, AI-based safety system where artificial intelligence will help in predictive maintenance, real-time diagnostics, and decision-making during emergencies. Next is active feedback loops, which a sensor placed on the train and guideway can continuously measure the gaps between them, feeding real-time data and on-board computers that adjust the magnetic force, which can help stabilize the train. Third is to increase the speed of maglev beyond 600 km per hour, which can lessen the time to arrive at destination and also increase the efficiency of the train. Addition to that, supercontinent connectivity can be done, which includes linking maglev to other continents such as Asia, Europe, or North and South America, which can revolutionize long-distance travel. This can provide with people other alternative of travelling other than flights or ferry to go to their destination, while also able to enjoy the scenery along the train ride. Lastly,
an alternative levitation technology which combines Maglev with existing rail technology. This will help to lower the cost of Maglev projects instead of building a whole new rail from scratch, and help other countries with limited infrastructure to also be able to experience Maglev in their home country.